All right.
Okay, let's get ready and started. Welcome, everyone. Thank you for joining us today. I'm Brunella Rodriguez, assistant professor at Clemson University, working with wood utilization and biomaterials, and along with Shiping Wang, and of course, facilitated by Forest Products Society and UFRU Forest Products Division, we are happy to present this webinar, having Dr. Geoff Downes as our guest speaker for today. And before we move forward, I would like to show you the Forest Products Society website and tell you a little bit about the technical interested groups. And if you are a member, you can access these and be part of the discussion boards that we have there. So the goal of the FPS TIGs is to facilitate communities connecting more often than just annually at in-person conferences. And it's also a way for you as a member to add more value to your membership. So far, we have nine TIGs already established, and among them we have the processing and wood quality chaired by Scott from Oregon State University and myself, and the other one is non-destructive testing and evaluation chaired by Shipping and Munkaya. So if you are interested in delivering a presentation in our TIGs, please contact us and we will send you more information about it. I would like to highlight two upcoming great conference for next year, 2024. One is the annual conference, the Forest Products Society conference. It will be in June next year in Knoxville, Tennessee. And the other one is the International Non-Destructive Testing and Evaluation of Wood Symposium. It will take place in September 2024 at University of Campinas, Brazil. I really encourage you all to check both websites for more information. So with that said, I will turn it over to Shipping. Thank you.
Thank you, Brunella. Thank you all for joining the webinar today. I'm glad to have many people come into the Zoom and join us from different parts of the world. My name is Shiping Wang. I'm a research engineer at the U.S. Forest Service Forest Products Laboratory. I'm also the chair for the technical interest group, RD&E technical interest group for Forest Products Society. Before I introduce the speaker today, I just want to acknowledge the sponsorship of UFRO, International Union of Forest Research Organizations. For those who are not familiar with UFRO, UFRO is a global network for forest science cooperation with more than 15,000 scientists participating in the network from all over the world. Today's webinar is co-sponsored by IPS and UFRO Division 5, which is a Forest Products Division, and also the Wood and Fiber Quality Research Group. Currently, I'm the coordinator for this research group. Just for your information, Bernardo, can you move to the next slide? Yeah. Next year, there will be a UFRO All Division Conference. Will be held in Stockholm, Sweden in June 2024, typically called the UFRO World Congress. There will be many technical sessions related to forest products. And our Wood and Fiber Quality Group also organizing, hosting a technical session related to silviculture, forest genetics, and wood fiber quality. So if you're interested in this conference, you can check the website for details. Next slide. Today's speaker is Dr. Geoff Downes. Geoff is the director and a senior researcher of a research and development firm based in Tasmania, Australia. Geoff specializes in developing and operationalizing non-destructive wood quality assessment technology in commercial plantations. Geoff has been involved in studying the causes of variability in wood properties for 35 years, which is a long time. And he has been focused on the physiology of wood formation as affected by environment. Geoff has also get some involvement with the application of a civil scan to forestry since starting with the CSIRO in 1992. This work involved using these high-resolution wood property measurements together with the tree growth monitoring to investigate the links between environment, growth, and wood variability. Since 2018, Geoff has led and collaborated in many projects to evaluate the commercial application of resisted drilling in plantation inventory, develop a web application to facilitate uptake and generate commercially useful metrics from resisted graph profiles, and also explore the limits and factors affecting the accuracy and precision of resisted drilling measurements. So with that, I'll turn over to Dr. Geoff Downes for his presentation.
We should be away. So is that coming through for people?
Yep, it's already showing. Yep.
Okay. Well, thank you for the opportunity to speak here this morning. Well, morning for me and evening and afternoons for many of you. And first need to apologise for last week. That was purely my fault that I didn't understand the time zone differences as I should. So thank you for coming back. In this presentation, I'll provide an overview of the work that we've undertaken over the past 7 or 8 years around the topic of resistance drilling for non-destructive evaluation of the standing tree wood properties as it applies to routine forest inventory applications. And that's the key focus, is how can we actually develop a non-destructive assessment for wood quality that's affordable and sufficiently precise and accurate for routine commercial forestry. Before starting, I'd like to acknowledge my co-authors in this, John Harrington, Marco Lorberg, both of them in New Zealand, Jen Villis and David Lee up in Queensland. And we've developed quite a cohesive team over the last 4 or 5 years that is backing up the industry uptake of this resistance drilling technology. So around 2015, we set out to establish the accuracy and precision of resistance drilling. You know, was it useful? Does it generate meaningful data? Is it as good or better than existing methods? And to date, the most accepted method for non-destructive sampling of trees has been increment coring at breast height. And if undertaken at all, most commercial forestry growers use hand coring, which involves taking a small diameter increment core. And in Australia and New Zealand, this is typically just the outer 50 millimeters of the stem to provide an indication of the mature wood density of the tree. It might be assessing an individual core, it might be batching cores and just getting an individual density measurement for that particular plot or site. In the late 1990s, the tree core core was developed by David Spencer at CSIRO with the aim of trying to find a way to non-destructively evaluate plantation eucalypts. Because eucalypts are much less amenable to hand coring, and the plantation eucalypt industry in Australia was just taking off at that time. Tree core here is takes a 12 to 13 millimeter diameter core, but leaves a 22 millimeter diameter hole in the tree. Now we can take those cores and we can just simply measure them for basic density, and there's several different techniques that we can use for that, but effectively we're just taking the mass and the volume and generating a kilograms per cubic meter value. Often species need to be resin extracted, particularly the southern pines up in Queensland. And alternatively, though, we can actually take that density measurement, or that density measurement is actually useful to give you an indication of wood quality of the trees from a plantation point of view or processing point of view. But we can take those cores further, and we can run them through technologies like SilverScan. SilverScan has been around for 3 decades, and it's still the gold standard technology for the detailed measurement of radial properties of many key wood properties. Even though this was taken from a SilverScan 1 sample back in 1995, this is the sort of detailed information you can get: pith to bark measurements of cell diameters, density, and then calculating coarseness and wall thickness and other properties like that. One of the unique features of SilverScan 2 and 3 was its ability to measure microfibril angle and with density predict dynamic stiffness, dynamic MOE, and that's been well established in the literature. But even measuring core basic density is too expensive and too slow and too complicated for a routine commercial forestry application. I was told by a tree breeder back in the early 2000s that a wood quality measurement has to be no more than $5 per tree per property. And then a few years ago, he said basically $5 per tree for all the properties you can get. So we needed a cheaper method. And this is where the resistance drilling came in, using the IML PT series power drill. We're not the only ones who've been working on this. The people at Cancor at North Carolina State Uni have been doing a lot of work with this as well. I'm not really familiar with the details of their work, but it's been used by, focused on by a lot of people. It's been around for several decades, and for the past 7 or 8 years, it's been our focus for us to establish its accuracy, precision, the robustness of the technology, and the ease of use. We've then wanted or needed to be able to demonstrate to our industry partners that it does provide commercially valuable information. And then once we've done that we need to develop an easy to use method to rapidly process measurements from large numbers of trees. So resistance drilling works by taking a 3mm drill needle and measuring the power that's required to drive that spade drill bit through the tree at a constant forward speed in RPM. You can actually measure the resistance to forward movement as well, but the main thing we'll be focusing on here is that resistance to turning. The torque applied to the needle is the main measurement, but there is also the opportunity to measure this forward movement. As the needle progresses through the tree, variation in the power that's required is measured as amplitude in the percentage units. So this on this axis here is 0 to 60% of full amplitude. And it's measuring that amplitude every 0.1 millimeters of forward movement. One effect is the action of friction. So as the needle drills through the tree, a needle or friction on the needle shaft, and as you can see, the baseline here as it emerges from the other side of the tree is somewhat off the baseline. So we need to be able to account for that action of friction accumulation of the needle as it drills through the tree. Currently, we assume that to be linear, and we apply a baseline correction to get rid of it. And then the mean amplitude of the trace is related to the density of the material, particularly between the underbark portions of the tree. So what we have found, focusing on radiata pine, but also doing a lot of work in eucalypts, is that resistance drilling is fast and precise, and it's sufficiently low cost that it becomes commercially applicable. We have found that a single operator can conservatively measure 400 to 500 trees per day. Some of the tree breeding applications in Australia have exceeded 1,000 trees per day. As well as providing a mean density value, it also provides information about the radial patterns of variability. No laboratory work is required. So basically you can drill your tree, you can process the traces and get the data you want within 24 hours. The Resi equipment is easy to use, and it is a strong predictor of basic density. So we've got a couple of examples of that here, where on 600 trees taken from the North Island of New Zealand, we're measuring 85% of the density from the outerwood basic density cores that we took to calibrate the instrument. if we reduce that down to plot means, then we're getting over 90–95% of the variance. Genetic correlations are basically 1. So when when people have used these data for genetic correlations of basic density, then the values are basically 1. Varying forward speed in RPM has an effect on amplitude. And this work is work that's been undertaken by a postdoc fellow of ours, Phyllis Genvillis, exploring the interactions in logs from 6 different species, which represent very different basic density material. The outcome was the effect of these sampling conditions can be compensated for to produce a standardized trace. So we hope to publish this work soon, but it allows us to identify the optimal conditions to use for different species. And that's based on the volume of wood derived by a single revolution of the drill bit. And that's based on a lot of the excellent work done by Sharapov in Russia in this application as well. So basically following the same sorts of techniques that he's used. So if we look at what we need to facilitate the uptake of the commercial partners of this technology, and our partners are both commercial plantation growers and sawmill and other processors, we need a software tool that is fast and easy to use. And this was the critical factor for commercial uptake. This tool needed to be able to automatically determine if the Resi trace has gone right through the tree and emerged out the other side, or whether it's only a partial diameter. For example, this tree, the second from the top here, at 400 millimeters, it was a PD 400 instrument that we used. It couldn't get right through the tree, and so the software needs to be able to determine whether we've got a full trace or a bark-to-bark, what we call a bark-to-bark trace, where it goes right through, or a pith-to-bark trace, where it only goes part the way through, and really it's only entry radius that we focus on in these trees. It needs to be able to account for the effect of needle drag and do a linear baseline correction to bring the trace back down to this sort of unaffected level. And it's this baseline corrected trace that we actually use for measurements. So within our commercial species, to convert this amplitude variation to density, it's basically a linear relationship. So we need to be able to then calculate the relationship between amplitude and basic density, define the slope and the intercept for that simple linear regression relationship. So this is an example of the user interface of the current version of the web platform. And I hope to demonstrate the use of that platform at the end of this talk, just for a couple of minutes. Individual traces are uploaded using this upload button here and automatically processed. The most traces uploaded to date in a single run that I'm aware of is around 5,300 from a Euclid genetic breeding trial. And depending on internet speed, the upload can take various amounts of time, 5 to 10 minutes, maybe longer if you're in a really slow, got a really slow connection. Each line in the summary table down here represents a single Resi trace. And if you click on each line, then that trace will be displayed in the plot window at the top. Once processed, the data can be saved as a Resi file, so that all the individual traces that you've uploaded can be saved as a single Resi file. And this is in the RDS format. So if you're used to programming in languages like R, then you can read that directly, that Resi file directly into your R and do any further analysis you want. And that Resi file saves all the traces plus this summary table plus annual ring or interval ring data, which I'll explain in a minute. Many of our commercial users find that just uploading the traces and downloading the summary table is sufficiently precise for their needs if they're looking at generating a plot mean or a compartment mean. And so most of our Australian commercial users are just uploading the traces, downloading the summary table, and using that data as it is. However, there are a lot of options here for manual intervention of traces or manual editing. So we can do things like change the here, represented by this green line. We can change the position of the entrance. We've got a zoom button to zoom in. And we've also got another tab up here, remarking tab, which I won't have time to explain, but it also provides additional options for measuring, entering annual ring values. So one of the things we have is measuring annual rings, and the software does attempt to identify annual rings, but we have found in our particular species here, particularly eucalypts, which have very little annual ring structure, that it's very difficult to get a clear annual ring pattern in all the trees, in all these sites, and then to be able to cross-match them to get the same annual data for that particular part of the tree's radius. And okay, is anything here?
No, you're good.
Okay, good. Okay. So the platform makes an attempt to automatically allocate the annual ring boundaries, but they can also be added or removed through editing. But typically most commercial applications don't worry about the annual ring data at this stage. It's too difficult and it takes too time consuming. Because we've found the clarity of the annual rings to be difficult, we have got these options here in this particular part of the trace platform to, instead of measuring annual rings, you can actually measure them as intervals. And so you can generate 10 millimeter or 5 millimeter or 25 millimeter intervals, or you can measure intervals as percentages, 5, 10, 20, 30% intervals. For example, in this particular trace, it's the same trace that was processed last time, and it's been divided into 5% intervals. So we've got 20 intervals from pith to bark. And if we look then at the annual ring tab in a web platform, we can actually show the radial variation from pith to bark of the entry radius or the exit radius, and you can retreat and advance. And the summary table here has a line for every interval, for every radius of every trace that you've uploaded. And that, again, can be downloaded. But if it's present, it's also in the Resi file here that's saved that can be accessed directly via R. There are different properties that can be measured. We've got the mean, the standard deviations of each interval, the coefficient of variance, and a cumulative density trace. So as if you can display the data as a cumulative density. Various metrics, well, just as an example of one application of that. So here's an initial stocking of the effective initial stocking on a 16-year-old Pinus radiata plantation in New Zealand. And this data was sent to me by an industry partner in our project. And when they'd resied the traces, when they'd resied the trees, they'd found no effect of stocking on mean basic density. So if they looked at the mean basic density of the resi trace, there was no effect of stocking. But if we look at it from the point of view of these 5% intervals, then we can see that each of the 4 treatments, from 33 stems per hectare up to over 2,000 stems per hectare, the radial trajectories are quite different. And they are starting to separate out into different outerwood densities by the age of 13, 14, 15, 16. This is when we express the data in terms of distance from pith, and the advantage of this method is that you can easily average over plots and treatments to using the same interval, and that assumes the same sort of growth pattern. But every interval also has a radial position, so we can plot exactly the same data as a radial position from distance from pith. And again, we can start to see the difference in patterns. What was unique about this study is that they'd done some time of flight acoustic testing on the standing tree at harvest, and they had found significant differences in the outerwood acoustic velocity. And if we look at the Resi data in this way, then the arrows represent the order of differences between the acoustic velocity measurements of the trees as well. The website also includes a simple soaring simulator. And this is not intended to simulate actual soaring patterns. If we're working with a radius, then we're only getting we can turn that into a perfectly symmetrical disc, whereas most logs are not perfectly symmetrical. But it does mean that we can explore the interaction between density and predicted stiffness within the context of radial variation patterns. So you can express the data in looking at these virtual boards, or in this soaring simulator value, where we're just trying to calculate the volume or the area in the disk of different board classes for MGP10. I'm not sure if that's familiar to non-Australian New Zealand growers, but that's the grading systems for our boards that are produced. We've also undertaken a number of sawing studies with our sawmill collaborators over the last few years. And I just want to show some of the results we've been getting from that between the Resi predicted stiffness based on a density model and the actual mill data that's coming out of the green mill or the dry mill of these mills. So back in 2015, this is our first attempt at relating Resi traces taken and comparing them with trees that have been cut down from those sites. So this is pre-harvest Resi predicted stiffness against the green board MOE data. And we're getting 73%, and this particular Oberon study in northern New South Wales in 2019 was 83% of variance from pre-harvest Resi predicted stiffness, explaining commercially useful amounts of variance in the green mill. And in this particular Jubilee mill in Mount Gambier, it was 65% variance in the dry mill, going right through to the dry mill. Resi has also been useful for measuring the volume of boards. So obviously the DBH, the diameter of breast height of the tree pre-harvest, gave a good indication of the volume of boards that you would expect from that particular site as well. And we're finding even our tree breeders now are starting to use the Resi DBH instead of getting in close and personal with the tree and getting their eyes poked out by branches. They're actually and trying to use a Resi tape around a diameter tape around the stem. So they're using Resi DBH to get both overbark and underbark diameters. And again, the density versus a board MOE is 77% of the variance in that study. The website also has a user manual embedded in it. There are several revisions in that, and I've got to update for the current version, but that should explain most of the controls in the website, and you can easily download it or visualize it. There are a number of appendices, and the first one was one that was added at the suggestion of our industry, was a suggested approach to get you started and how to process the traces, how to get the best data out of it. Field work guidelines for using the Resi to make it safe and useful, what the Resi, how to look after your instrument, and the protocol for measuring cores to calibrate the Resi values is in there as well. So in summary, we have found that resistance drilling is becoming a routine practice for our Australian plantation growers, and a lot of our sawmill processors are trusting the data and even starting to ask for the data of the trees that they're about to get through their sawmill. The pre-harvest assessments are being used to inform the sawmill process and to help them manage log supply. It's being used in for screening breeding populations and often replacing or extending the more expensive measurements. And it's being used in both our softwood and our hardwood plantations here in Australia, and increasingly too in New Zealand. Our current research focus is on mid-rotation stands. How can we predict harvest age value and volume from measurements that are made in mid-rotation, or how early in the rotation can we get a reliable indication of what the harvest age value and volume will be? And exploring and extrapolating the radial trajectories. How can we take that radial information that SilverScan, that Resi provides? So I just wanted to now take you through the actual web platform use. Brunella, can you see that? Is that clear still?
Yeah. Mm-hmm.
Okay, so if we upload, we can go to the web platform, we can browse through, pick some Resi files, and I'm going to start off by picking a well-behaved set of traces, only just 10 at this stage. It uploads, processes them, and populates the table. So you can see here, we've got the interval percentages automatically selected. So it uploads and calculates 10% intervals from pith to bark. It gives you summary information in the window there about that particular trace, so that you can actually easily see it. And we can actually step through and check And for example, in this pith to bark, where pith to bark is just recording the trace type, which means that it didn't drill right through the tree. And you can see that the software has a go at trying to identify where the pith is. So we can change that pith position, and we can correct it if we want to, and it will record the changes up here. If we did want to have a go at marking annual rings, we can just select annual rings and rerun them. And now it has a go at putting in annual ring boundaries. You can see here that it's missed a ring for one reason or another, and so we could add a ring there. We can actually see it's got a double ring there, so we could actually click the zoom and take out that ring. Sorry, got to go back and add the ring, and then double click to get back to the trace. And we can advance through the traces as we go. Not all trees are that amenable. So we do have some examples, some problem traces here. There's a couple of acacias that were sent to me by a customer. And what they'd done, they were young acacia trees, and they drilled right through the tree and into some sort of branch or something at the other end. In which cases, you can see it's gone right through the tree. We can actually then turn that from a pith to bark type into a bark to bark by selecting DOB and then clicking where we think it's emerged. And that will change the trace type into a bark to bark type. We can also delete that tail portion if we wanted to. And we can do the same for the next tree. If we wanted to have a look at what some of our young eucalypt look like, then these are selections from different Resi instruments. And so the software actually records the Resi instrument code so that you can actually see which one it does. And you can see they've all got different serial numbers here. And it records all this sort of information in the web platform summary tables, so that if you come back to a data set after a year or so, or a couple of months, you can actually use this table to identify the conditions that we use to process the trace. If we look at the annual ring data here, let's rerun that, and we'll turn that into 5% intervals and rerun. We can look at the ring marking of this, and obviously the rings are all the constant values, and we can, so I meant to look at this one, annual ring table. We can actually see the entry radius and the exit radius, the radial variation patterns of the intervals. We can pick that up. We can download the data and analyze it. And if we go back and just run through this hoop pine example, we get some interesting traces that we programmatically have to deal with. So hoop pine has this interesting high density spike here. So the software has to be able to automatically identify these entry and exit cambial positions, despite these high density barks or various other things that can throw themselves at the code, and be able to automatically place the traces in the right, process the traces correctly. And just to demonstrate the, as a final, let's go back to just a couple of these. We can run those traces through the R sawmill application, and using the average of the entry and exit barks, we can actually then get a feel for the wood quality in those particular traces, depending on the trace, which has now been turned into a radial MOE trace or stiffness trace. We can actually look at the boards, and again, highlighting this is not attempting to be a realistic sawing process, and we're still evaluating the commercial value of some of these, but some of our processes actually do use some of the metrics in this table to decide whether a particular plantation is of value or not. So I'm going to leave that there and turn off sharing and hand back to Brunella.
Great, thank you, Geoff. Thank you, great presentation. And now we're gonna open our for questions. And can you see the questions in the chat, or we have one so far?
There's no question here. There's no question in the chat box.
There is one.
Oh yeah, there's
so the person wanna ask about how many samples is needed to create an accurate models in the site for different tree species.
Depends what you mean by models. So in terms of generating a relationship between density and amplitude, we would typically take 25 to 50 cores, and as long as they cover the sort of range of densities that you're going to get in your population, that's fine. That should be adequate. We've done a lot of studies. Again, Willis has been working on this with David Lee up in Queensland, to look at between instrument variation, between that Resi density and amplitude over time. IML have actually seemed to improve their calibration technique, so we're finding very little, relatively small amounts of variance between Resi instruments, maybe 5 or 6 kilograms a cubic meter. Maybe if you're talking ranges, 95% intervals, we're talking plus or minus 8 kilograms a cubic meter between instruments. And they seem to be very good at now, once they come back from their annual service, we get very constant relationships. But in terms of models, once you've calibrated your instrument as a density predictor for that tree, then that should be adequate. Yeah. It's not like near-infrared spectroscopy where you might want to have a couple of thousand chemical spectra in your calibration. It's a different, it's just a simple linear relationship.
Thank you. So I actually have a question. So when you're using this tool to select progenies for tree improvement programs, how could we use it in the best way to select, I mean, clones or progenies? So is there a big difference between pine trees or eucalyptus trees when we are using the resistographic tool for that?
Well, most of our tree breeders now are pretty well, as I understand it, measuring every tree in the trial now. So I'm not quite sure if I understand the question fully, but effectively, the more trees you're measuring to get your genetic correlations, the better. And relating that, previously, if you're only coring, then you'd be taking a subsample.
Okay.
No, Avenji is asking, is the software free? Because I'm self-employed and I've spent many thousands of hours writing this, there is a charge that I charge. So I have a number of companies that pay an annual user license for that thing, and I'm happy to talk about that offline. If it's just research providers just needing it for a short period of time, then we can arrange application access under various conditions. But the charges are relatively low from a commercial point of view. I still need to be able to fund my, well, typically the user access fee covers access, but also covers my support, keeping the platform current with changes in IML firmware and that kind of thing. And just people often send me difficult traces or something gone wrong, and I can fix it pretty quickly. How often do you replace the needle in order to maintain good calibration with wood density? Thanks, Joe. We started off advising replacing the needle every 1,000 traces. And that was we're trying to be quite conservative. The work that we've done via Willis's postdoc now suggests that in radiata pines, southern pines, maybe you can get 2,000 trees as a conservative average. If you go back to the work of Angie in a few years ago, when looking at how many meters of wood have you actually drilled is probably a better approach, but it's much harder to regulate. So when we looked at those different trees from those Carimbia, those CCV trees down to hoop pine, and we were looking at logs that were up around 700 to 800 kilograms of cubic meter. Again, if you're using 5,000 RPM and you're doing lots of rotations, and that you'll need to change your needle every 300 meters of usage. But for our radiata pine and southern pine trees, which are a little bit more dense than our radiata pine, 1,000 to 2,000 trees would be adequate. We're dealing with this. Okay. And do holes need to be repaired to minimize insect or other damage? No, we haven't. Again, it comes back to particularly with pines, they're very good at bleeding into any holes. Often when you come out and you've taken your needle out of the tree, it's really hard to find where you actually drill. And if you're coming back to it after a period of time, often it's the resin bleed. It shows you where the hole is. Otherwise, you can't find it. In eucalypts, it's very, very hard to find. Adverse effects from the 3-meter hole left in the tree. We haven't had any complaints from the trees yet, but obviously you're leaving a hole in eucalypts, you've got the potential for decay. As with any invasive technique, radiata pine, southern pines, I think the resin bleeding is probably going to be as effective as anything at minimizing any decay or opportunities for bugs to get in or whatever.
So Geoff, before we go to the next question, Joel, do you have other question? I think you start to talk and.
No, I just want to say thanks, Geoff, and good to see you again.
Yeah, good to see you. So I was just wondering, are the conversion efficiency in the standardization suitable for all tree species, or would they have to be adapted for different species? Also, how would the linear friction coefficient deal with reaction wood? Would it just remove the additional density from reaction wood at the same time as the friction? So no, well, let's start off with the reaction wood or compression tension wood. It doesn't remove the baseline correction doesn't remove the compression wood effect. You'll still see that. It just simply removes that that baseline friction. Compression wood, tension wood are quite different in their characteristics, so I would expect they might have effect on that linear relationship, as in we assume the relationship to be linear.
Pine and eucalyptus. So I would assume the friction would be affected by wood species, especially for hardwood. It's going to be different.
Yes. So yeah. So one of the things I didn't demonstrate in that there's a drop-down box in the web platform called Select Species.
Oh.
And the only thing that does at the moment is change the way pith to bark traces are baseline corrected. So we have a slightly different relationship for radiata pine, southern pines, and eucalypts as to how those pith to bark, where we don't have that flat line coming out of the tree to determine what that accumulated friction is. We have a linear model that is a function of diameter and density, and the coefficients of that model vary between species. So in that sense, yes, it's very easy to generate those coefficients for the population that we have, but we can actually adapt that baseline correction for different species.
Yeah, that's good. It seems we need a database for many different commercial species.
Mm-hmm. Well, again, it was a question of knowing how much effect it has. So are we dealing with 2 kilograms a cubic meter, or dealing with 20 kilograms a cubic meter? What do we need to do? What do we what can we get away with just not fussing about?
The one other question is about so in the wood inventory in Australia, wood quality inventory in Australia, when you do the resistor graph measurements, do you collect the full length the resistor profile or just partial resistor profile?
Typically, we advise going right through the tree if you can. So that's a full diameter profile trace if you can. The advantage of that is it gives you both sides of the tree to get a density estimate from. And if you're doing any radial or sawmilling data, virtual sawmilling data, it gives you 2 radii to work with. And also because your baseline correction is then much more robust, and also DBHs. So because our industry are also now using a lot of this DBH data off the Resi instrument, a full diameter trace gives you that. And that's where a lot of our Queensland growers with the southern pines are quite big. They're going to PD 500s, not PD 400s. That gives you a 500 millimeter trace rather than a 400. Our tree breeders are often using 300 millimeter PD 300s. Bit easier to use around the younger small diameter trees.
Geoff, in the first few slides, you showed the wood core samples. The concept of after wood, 50 millimeter core samples.
Yep.
So basically, that of course that has a pretty good correlation. The resistor Resi profile amplitude, good correlation. How useful is that to the forestry companies? That information.
The 50, just the Resi data or the diameter core data?
After core, after wood density.
I think it's very useful in terms of just ranking sites and giving the processor an opportunity to understand how much MGP10 or structural grade stiffness that they can get out of a plantation. So it actually is very useful. Just the cores are difficult to get from a cost-effective point of view. So I've got a question here on looking at circumferential variation with resistance drilling. Yes, there is circumferential variation, and Resi can be very good at doing that. When Villas was doing those logs and he was collecting 800 traces of different aspects, and so we've got some very good information about how the wood density varies circumferentially in a few of those logs. And so yeah, there is circumferential variation, and that's why when we're sampling out in the forest, there's the question of how many traces do we take per tree, and how many trees do we measure per plot, and how many plots per compartment or per hectare. And we're finding that, well, as in with a lot of dendrochronology work, you're better off taking more trees than more traces per tree. And you only really need to take 10, maybe 12 trees per plot to get a good indicator of the wood density of that particular plot. And much fewer plots per compartment that you would expect than I would have expected to be coming out of our commercial studies. So Joel Jones, just a comment for holes, there are a number of papers I recommend if you want to look after healing the tree. And yeah, so there's a lot of work that's been done on how to fix the holes, but yeah, or how to deal with them. So any thoughts on correction or compensation techniques for spiral grain effect on MOE? Not using the Resi. Resi is really good at measuring density. It doesn't measure microfibril angle. It doesn't measure spiral grain. It doesn't measure moisture content that we've seen. It doesn't measure heartwood boundaries. So there's a limited things to what it can do. Now that we've got this Resi hammer, we are using many nails to see what it can do, but we've got to realize that it's not going to do everything. But spiral grain is an interesting one because one of the issues you have with Resi is needle curvature. So as you're drilling through the tree, the needle can wander off the straight transect. And if you point the Resi down, the needle will tend to go to the right. If you point the Resi up, the needle will tend to go to the left. you need to keep it pretty flat to maximize your chance of going directly through the tree and coming out on the direct opposite side. And that's probably interacting with things like spiral grain and that kind of stuff as the needle's biting through that slope of grain effects. So yes, we're doing a lot of work on these sorts of things and answering a lot of questions, but also there's some questions we can't fully answer. I haven't got any more questions that I can see. Have I missed any?
I was double checking it, but I don't think so. Yeah.
So the web platform has probably processed over 1 million traces to date from all different sorts of species. It's been surprisingly reliable, I found.
I see Evgeny in the Zoom. Hi, Evgeny. Do you have any questions or comments?
Do you hear me? Hello?
Yes.
Do you hear me?
Yes,
Yeah,
we can hear you.
Yes.
Yes.
Okay, first of all, I would like to say thank you for the presentation. It is very interesting, and of course, I always, when you publish new articles, it is always interesting to read them. Yes, I have some questions, but maybe I will write an email later and ask some specific questions about the drilling resistance.
Okay. That'd be welcome. Yes.
So does anyone have more questions? That's the time. That's the moment.
Okay. If nobody has let's ask one more question maybe. There's an issue or challenge when using the resistance graph tool in the trees. Often it's easy, the drill bit will deviate from the radial path. I'm still thinking about to find some solution to solve this problem. So Geoff, have you thought about any method can help to improve the measurements from instrument perspective, not from software?
Well, we often talk about aspects of the instrument. I guess it comes back to the question of priorities and value for return for effort. So the wandering of the needle, if you're using it correctly and then maintaining a horizontal approach, then the wander of the needle doesn't really present an issue for the accuracy of the data at the commercial levels of interest that we're focusing on. Our focus is much more around identifying how we can develop the application to things like veneers, engineered wood products, and then other further aspects of understanding and modeling variation using Resi data input into growth and yield tables for forward forecasting. There's opportunities now to go back and evaluate all of the silvicultural trials that have been conducted that are still standing and look at the effects of fertilizer effects on wood quality and growth. So those are the sorts of focus that we have at the moment. Yeah.
Thank you, Geoff.
So it seems that we have one question for Jerry's. So
Jerry, if you want to come off mute.
Yeah. So my question I wrote in the chat, question chat was in two folds. It seems. Hello, can you hear me?
yes.
Can hear. now. Yes.
Yeah, my question was in twofold. Since Doc only answered the first part, the second part was I wanted to know if there's any correlation between opposing drilling profiles and how are they correlated?
Okay, I didn't quite catch the question. How will what correlated?
Like opposing, like from one tree, the opposing radar. So the profiles for the drilling resistance for opposing radars.
The opposing radii. Yeah. Okay. But they're all, yes. They're strongly correlated, but they can be different depending on the eccentricity, that kind of thing as well. So the other factor that affects the patterns and the different radii is how far you miss the pith by, and patterns there. So we are finding really good opportunities to look at within tree variation at that level. But one of our collaborators, Brian Rawley, looking at YTGen, he's been doing a lot of work on that sort of within tree variation, between tree variation, between plot variation. And there are significant differences, but they are relatively small compared to the plot to plot variations. So within tree variation, the opposing radii, there are differences, but they're relatively small.
Thank you.
I should notice, as you're being used the word resistor graph, you may notice I would talk about resistance drilling. There's some issues around trademark issues around resistor graph, which is Frank Rin's technology from Rintech, and Resi, which is the IML version. And I have had very little experience with the Frank Rin Rintech instrument resistor graph. I'm sure it's a very good instrument, very good technology as well. But,
Okay.
All right. Well, if there are no other questions, thank you all so much for joining. This has been a great and very informative webinar. So one last round of applause for Dr. Downes, our speaker today. And we will, as I said in the chat, we will have the recording available to all of you who registered and attended today. So we'll try to get that out before the end of the week. So look for that in your inbox tomorrow or Friday. But with that, thank you all so much for coming, and join us for our next FPS webinar. Thanks so much.
Thanks, Jennifer. Thanks, Vanilla. Bye-bye.
Thank you. Thank you, Jeff.
Thank you all.